Okay, next important concept, complex power. So we have a definition, first of all. This guy right here, and I forgot to turn my pen on. There we go. Turn the pen on. A definition. Star means complex conjugate. So if IRMS equals the its magnitude, I m, I'll call it m, at some angle phi of the current, then I star, complex conjugate, same magnitude, angle negative phi. Okay, that's the definition of the complex conjugate. When you multiply something times its complex conjugate, you'll just get Im squared. Okay, so moving along, the power can be written like this, Im star. So since the complex conjugate, you just negate the angle like so, it becomes the difference of the angles. And just using Euler's identity, we get this expression. The magnitudes times the power factor. That's the apparent power, that's the real power. And this is the reactive power. Right there. Active, reactive. They use the symbols P and Q. Okay. Let me do some erasing here. They're both in units of watts, which is the unit we use for power, and volt amperes, in other words. This is a diagram of how things work. So this is the real part. This length along here is the active power, or yeah, VRMS times this is the active power. Then this is the sine, this perpendicular to VRMS. Again, the inductive versus capacitive, real versus what happens to the phase angle with inductive and capacitance. Voltage leads current in inductive, voltage lags current in capacitive. Couple expressions. The magnitude of S, it's pretty easy to see. If you take the magnitude of this squared, you're just going to get VRMS IRMS. And the magnitude is going to be equal to this active power divided by the power factor. Here's another one. We can write it like this. The real parts and the imaginary parts. Resistance times the real part of IRMS, and vice versa. Now, we have impedance is equal to R times JX reactance. There we go. Just a couple of other identities. Now, the reason this works, that the power is going to be the active power, the real part of the power, it's going to be Z times IRMS squared. So the real part of it's going to be R times IRMS squared, but it's not going to be V squared over R. So another diagram showing how all this stuff works. Power equals I squared times the real part of Z. The real part of Z is R, of course. Okay. So for resistor, inductors, resistor, its power factor is exactly equal to 1. So that's your I squared R. Inductor, you will you'll always have 0 for the real part if it's an inductor, and capacitor 0 for the real part. So inductors and capacitors, they're all reactive. So here's the strategy. You have an impedance, and you can get the get V and I and determine, do it this way, finding the power factor, or the cosine of the angle between V and I, or the cosine of the impedance. You can calculate the real part of S. So power equals I squared times R, not V squared over R. Just remember that. Warning. There's the warning right there. That's because impedance equals R plus JX. So 1 over impedance does not equal 1 over R plus some imaginary stuff. It doesn't work that way. This works though. Okay, so let's do an example. And we have the load is consuming this much with this power factor, and we want to know the, let's see, VL, the V at the load is 220 volts at 0 angles RMS. The Z is this, and is that the Z of the load? No, that's the Z of the line. Right here. Frequency 60 Hertz. So, and we have this much power factor. So we want to figure out the voltage and the power factor to supply. We need VS is what we're trying to find. So picking up with this problem. So we know the power, the load is 20 kilowatts. Let's see, do I have a pen up? There we go. 20 kilowatts, power at the load, power factor is this much. The voltage at the load here, the impedance of the line, that's these two guys here, and then the frequency. And actually you don't need the frequency for this problem. You're given the line impedance. So it's inductive, that is the current lags the voltage. The angle of voltage minus the current is positive. Or the voltage leads the current, let's put it that way, inductive. Capacitive, just the opposite. Voltage lags the current. So the power, the 20 kilowatts, is going to be the real part of S, which we can write like this. It's going to be the magnitude of S times that power factor, or 20 kVA. So that the magnitude of S is going to be the 20 divided by 0.8, or 25 kVA. That's the magnitude of S. We can get the Q, so we have the P, 20 kilovolt amperes. We can get the Q from Pythagoras equation, Pythagorean theorem. And 15 kVA is Q. And now we can write the complex power. And It's 25 at 36.87 degrees. Let's see, I'm going over to new octave. Did I do that? No, I didn't. I didn't calculate that in new octave. So we'll go back to here. The next step then is SL is going to equal VL times IL star. IL star is a complex conjugate. So we can write it like this. The 25,000 at this angle, SL, divided by the 220. And I did check it with new octave, and this is correct. And this is correct also. The complex number notation and the magnitude and phase angle notation. So, the source voltage then is equal to the 220 at 0R at 0 plus IL times the impedance. And crunching numbers, again, I checked this with new octave and this is correct. So now we have the source voltage. It leads IL, let's see, there it is. The power factor is going to be the difference in the angles between the two, or approximately 40 some odd degrees. And working it out, 0.746. So, and again, I checked this out on new octave, it all works. And we're going to stop here and go to the next video.